Okay, today I would like to give another tutorial on twist and spatial velocity and the screw axis. I think in the previous lectures, I didn't make myself very clear, and based on comments and the questions I received after class, I think there's a lot of confusions what twist and screw axis really mean. Because these two concepts are super important for the screw theory based robotic kinematics, I think it's worth time for us to go over that again. So for those who already understood this, so then bear with me. This will be another alternative view of introducing those concepts. For those who hasn't really understood yet, this can be viewed as a standalone introduction again for spatial velocity and twist. Okay, I will be fast this time, like a tutorial. First of all, let's all I want to do is try to give a detailed introduction about spatial velocity and the twist first, okay? The first thing I want everyone to know is that twist or spatial velocity is a velocity of the whole rigid body. Okay, that's the very first thing you need to know. It's not I'll say it's not a velocity of a particular point in the space. Okay, it's a velocity of the overall body. However, the body has infinitely many points, and each of these points have a different velocity. So how should we characterize the overall velocity? How should we define it? Okay, let's look at this figure, and this is the rigid body. And suppose it's rotate about this axis, and also it's also moving, right? It's also moving in the space, also has translation motion. And we have a lot of points on the body. I denote them as P1, P2, P3, all the way to P100, 1,000. Okay, and each of these velocities are different. And the first I would like to point out, okay, so all these velocities VPIs, are not independent. There's some kind of relation among of these quantities. Okay, that should be clear, right? And however, they can be, so for example, this velocity VP1, if we know VP1, we will be able to know certain information about the VP2, depending on what's the relation between the location of the point P1 and the P2. In general, it turns out for all the velocities, I can write them as a function of where the point is, let's say P1, and also some other parameters, let's say parameters. Okay, and the same kind of relation holds for all the points. This is a per P3 per. Okay, so in other words, on the rigid body, any kind of point velocity that depends on the point's location, where it is on the body, and also depend on other kind of things. We call it parameter here. And this parameter is common to the whole body. So those parameters are common or the same for the entire body. Okay. So in other words, in order to know its point velocity, all I need to know is where this point is and a set of parameters, and this set of parameters, we can define this set of parameters as the rigid body velocity, okay? In other words, this is just a twist or spatial velocity is just one way to parameterize, okay, the rigid body's motion. So let me summarize that again. So this is, all this velocity can be expressed by the same set of parameters. Okay, I call these parameters. And the twist or spatial velocity is one set of the body is one such set of parameters, or one such parameterization. Okay, I hope that's clear for now. And how do we find this parameterization? Let's take a look. How do these linear velocity of the points relate to each other? A very trivial case that everyone should be able to understand is that, let's assume, first of all, okay, let's assume we know one velocity. Let's call that p0 here. Okay, let's assume p0 is on the rotation axis. Okay, and it's body fixed. Body fixed only means it moves with the whole body together. So the question is that, how do we use its linear velocity of vp0 to express other velocities? All we need to know is the following. Then any points, any other points on the body, any other, let's call this body fixed points, its linear velocity vp1, let's say vp1, equals to vp0, the linear velocity here, and the relative motion to the vp0, because it's also rotate about p0, so it's a plus omega cross p0 p1. Okay, this vector. I assume that's okay for everyone. That's physics. Okay, and similarly, we will have vpi, all the body velocities can be written as vp0. That's a velocity of p0 on the rotation axis. This p0 does not have rotation motion; it only have a linear motion part. And if you are not on the rotation axis, you have other rotation motion that will be characterized by omega cross p0 pi. Okay, so let's call this formula 1. So we can use, in this formula, we can think about this. Okay, this guy, let's use this. This guy basically tells us the location of point pi relative to the point we're referring to, which is p0. And the other two, these two, are the parameter we're looking for. If we know vp0 is the velocity of, what I called that before, a reference point, okay? Velocity of the reference for p0 and the angular velocity. If we know these two parameters, okay, two things, then we can express every point's velocity using the same formula, this equation 1. Okay, now the question becomes, we need a little bit more generalization. Okay, so that's what if we use VQ as the reference velocity for arbitrary Q on the body, Q on the body, or body fixed point, okay, for arbitrary body fixed point Q. In other words, I randomly pick a point, let's call this Q. This Q may not be on the rotation axis, okay? May not, let's say, I don't care. So may not be on the rotation axis. Okay, so if I choose my reference point, let's say I didn't select the point P0 and I select another point on the body, but it's also body fixed, I can the conclusion is the following. As first you tell the answer, I think we already discussed that before. The conclusion is that we still have the same expression or formula. In other words, VPI, if I want to express all the points velocity, still have the same kind of formula, which is VQ. It's not VP0 anymore. It's VQ plus omega cross from Q to the bodies, to the points location. Okay, so again, this one is point location, and this is my parameterization. And the formula is the same. Okay, and why is that? I think we derived that before. Let me briefly mention that again. Why this is the case? We can use, let's try to use P0 with a point on the rotation axis. Let's use P0 as an intermediate variable. Okay, we can express because Q is body fixed. Because we select Q, arbitrary Q, all we assume is body fixed. We didn't assume it's on the rotation axis. Because this is body fixed, by equation 1, we know we can replace Q. We can replace the PI by Q, and then we know VQ is body fixed, so it can be written as a VP0 plus omega cross what? P0 to Q, right? This vector. And then we replace this again. We use this equation again. We know this VP0 is just VPI minus omega cross P1 PI, this vector. Okay, and now we copy this down here plus omega cross P0Q. All right, we cancel this out. We group these two terms. This one will give us exactly this formula. Let's call this one equation 2. Okay, I hope that's clear now. So no matter what point I pick, if I know this body fixed point linear velocity, I know the angular velocity, then I can use the same equation or same formula to express all the body fixed points velocities using this formula. Now the confusing part arises. Okay, let's look at third case. Now let's directly consider a frame. Let's consider a frame A with origin O of A. Okay, let's draw this here. Maybe this will be our A. Let's call this A. It's frame A, and this is origin of O of A. I randomly pick a frame. There are two possible cases, right? Let's first look at the first one. Let's say a simple case. Let's say A is, let me change back to the light color. Let's say A is body fixed. Let's assume that's the case. Okay, first case. Let's say assume A is body fixed. What do I mean by that? Is that this A frame rotates and moves in the same way as the body. You think about this one is rigidly attached to the body, so it moves exactly the same thing, same way as the body. So it's body fixed. That means it moves with the body. In this case, we can just let OA equal to Q in equation 2, right? In equation 2. Then we can get, so by let's say by 2, equation 2, we know V of OA, any other points on the body, VPI can be written as, if I choose the origin as the reference point, then I can say this is VOA plus omega cross from OA to PI. The same formula, nothing changes. It's just I choose OA as the point Q, because I said before Q can be arbitrary, right? Now OA moves with the body, so OA can be thought of as the Q, as in equation 2. Okay, in this expression, if we know in coordinate systems, in A coordinate systems, if I express this physics, so that means VPI in A, that's velocity in A, VOA in A, plus omega in A cross OA to PI is the point vector representation of the point PI in A, right? So that will be just PI in A. So for Buser notation, for shorthand notation, typically we'll just say VP, any point, let's say VP equal to VOA plus omega cross P. If the frame reference is clear from the context, we'll just write like that, right? Any point velocity is the velocity of the origin plus omega cross P. Okay, that's clear in this case because the origin moves the same way as the body. Now let's think about the confusing part for some students. Okay, the second case. Let's say assume A is not, let's say not body fixed. It's not body fixed. What do I mean by that? A's motion is detached from the body's motion. There's no kind of a link between a frame and the body. So it could be cases that a frame does not move. It's stationary. Possible, right? It doesn't, or could be moves in other way. In the sense that A follows another motion, but the body rotates by itself. So these two motions are uncorrelated. It's fine as well. The question is this part, okay? If A is not body fixed, what we should do? In this case, let's say the Q, let's say the body fixed point Q. Let's say Q, the body fixed point, right? Such that it's a body fixed point. Suppose there's a body fixed point, such that at current time t is equal to OA. Location-wise, they are at the same location, but this point is body fixed, but OA is not body fixed. You see what I mean? So OA is a location. Let's think about a location, but the body has a body fixed point currently just resides or located at this particular location. Let me just denote this equation, like let's call this star, all right? Then I can by 2 again, all right? If Q is body fixed, then I can use 2, right? By 2 again, by 2. We still know any kind of other body fixed point, PI. Its location, its velocity is still VQ. Let's say, now let's put the time index in, okay? VQT plus omega cross from Q to PI. I'm just copying down the formula 2, all right? Because of the star, let's say by the star, this one, we know because QT is just OA, right? So in this case, we know VPI equal to VOA plus omega cross OA, Q is OA, right? PI. Or in frame A, in A frame, again, VPI in A equal to VOA in A, omega in A cross PI in A. Okay, so let's write it down. Let's call this guy, this guy, equation 4. Let me claim 3, which is, let's think about 3. 3 is, where is the 3? Let's call this 3, okay? This guy, by 2, we got this guy. This is 3. 3 and 4 are the same. Okay, same. If, okay, if we define the symbol VOA in a special way, right? If we define VOA as the velocity of the, let's call it body fixed point, currently coincide with A, currently coincide with OA. So OA may not be body fixed, right? That's the point. In 3, that's the condition that OA is body fixed, so it rotates same as the body. And in 4, OA is not body fixed, all right? OA doesn't move. But in the twist definition, we still view this symbol has a special meaning, all right? It's the velocity of the body fixed point, which is Q, right? It is Q star, sorry, this star equation star, that currently coincides with OA. Maybe next time it does not, it moves away, okay? Will be another point will be coincide with OA, right? So that's exactly the explanation of coincidence, okay? That's the explanation of this sentence. This one, it just means equation star. Okay, well, there's a lot of confusion. I received a few questions, so I hope that can help students to understand these 2 cases. All you need to distinguish is 3.1 and 3.2. In these 2 cases, the OA is body fixed and body not fixed, right? But in both cases, we just redefine this symbol VOA as the velocity of the body fixed point currently coincide with OA, all right? If we just define that way, then the 2 equations are the same. Okay, then I can let's see. Now I can, in the summary, let's summarize. Okay, so given the twist, given the spatial velocity, let's just call it twist, they're the same. Given the twist, sometimes I may be not that clear about where the reference point is. Let's say omega and the V of R. Given this twist, now you should be clear that, let me repeat that again. This guy is the velocity of body fixed point currently coincides with R. Okay, R may not be body fixed or may be body fixed. That's 3.1 case or 3.2 case. It doesn't matter. We define this V of R as the velocity of a body fixed point currently coinciding with R. I hope that's clear enough. And this is, I often call it a reference point, but but it doesn't have really official name. Okay, if I gave a twist, you can conclude for any why it is a rigid body velocity, because it's a parameterization of all the body velocities, because they are all dependent, right? They are not free variables. For any body fixed point, let's call it PI, I can always write VPI equal to VR plus omega cross PI. That's the formula. If I gave these two things, omega and VR, okay, and with a special definition of this VR, not the usual way, okay, then I can write down all the body fixed point velocity in this way, okay. If to be more precise, I think this is let me be more precise. This is from R to PI, okay. Hold on. This is from R to PI. That's vector. And if I select, so let's do that more precise. If R point is origin of a frame, let's call it A again. Okay, if R is origin, then we know this will be the point representation of that PI in the frame A. So then VPI in A equal to VR in A plus omega in A cross PI in A. Okay, so that's the fact I want everyone to remember. And not only that, another thing is that this summary, given that, let's say this is 1, another one is 2. Because of this, we can think of the body. We can think, let's not think of. We can think, or we can view the body is translating at linear velocity VR while rotating, let's say rotating at velocity, sorry. At velocity omega about axis passing through the R. Okay. So mathematically, you cannot distinguish the motion that because I can pick, for example, okay, I can pick this frame and I can pick another frame B, right? And then I will have a twist in B. This is a twist in A. And mathematically, you can think of, if I represent in B, I can think of the motion is just with a linear motion V of OB, okay, and rotate about axis in the same direction of omega, but that axis moved to a direct axis where it passes through the origin of B. In the same way, I can think of this case as equivalently, okay, in terms of parameterization of all the point velocities, I can equivalently think about this motion is like rotating about axis passing through OA if I represent the velocity twist in A. Okay, that's the meaning. I hope that clarify a few things for some students. I'll give another example. I think in lecture 2, I gave several examples already. I just want to give another example to complement or support your understanding. Let's think about this case. Here is the spinning top, and it's rotate about the ZA axis at unit speed, right? So the direction is ZA of hat, this omega. Let's call it spinning top. This is spinning top, right? Spinning top. Its motion is just rotates, okay, about the axis. And let's pick another axis, frame B. Let's assume the frame B moves to the right that means in YA hat direction. The frame is moving to the right, but this motion is not really kind of related to the spinning top motion. They're uncorrelated, all right? So now I'm asking, what is the twist of the body in frame B? Okay, that's the question. So based on my previous introduction today, I hope that's clear enough. You can easily answer the question. First of all, OB in terms of its coordinate will be always in the x coordinate 0, y coordinate, let's assume originally it's also at 0, so it will be a times t. Okay, at time t, it moves a meters. So, and the z coordinate is that. So that will be the OB's location. Okay. And then if I want to know what about V top B, the spin top, of course, that will be omega in B and VOB in B. Okay. And we know omega is easy. That's the free vector omega. Expressed in B is also the same. It's 0, 0, 1. Okay, because ZB is the same direction of ZA. And also, now we need to know what about how to compute VOB. And based on our discussion today, or even previous lecture, we know that VOB is not how fast OB moves. OB moves to the right at speed 8 meters per second, but that doesn't matter. Okay, by definition, this guy is what? By definition, VOB in B, it doesn't matter in what, okay? So VOB in the twist expression is not how fast OB moves. It's the body fixed point where the fixed to the spinning top, okay, not fixed to the frame B. It's body fixed point location velocity currently coincide with OB. So VOB would be, let's say, VOB, because OB is body fixed, we assume it's a body fixed point, right? So VOB equal to, if I choose OA as a reference, we know VOA is 0. Okay, so if I use that as a reference, VOA plus omega cross from OA to OB, this vector. Okay, if I want to find a OB is not body fixed, but I assume there's a body fixed point currently coincide with OB. And so in this case, I can express this velocity as this body fixed point velocity. That will have the same formula, right? And think about the OB as Q in our equation 2. So that will be VOA plus omega cross VOA to B, right? If I use coordinate to express this, that will be in the origin is body fixed point is in the, it has no linear motion, only rotating. So VOA is 0. So it is 0, 0, 0 plus omega is 0, 0, 1 cross OAOB, right? That's the point coordinate in B, because B and A have the same orientation. So this will be still O 0, A times T, the time dependent now, and 0, right? So overall, I will have this becomes z-axis cross y. That will be negative x, right? Sorry, negative, yes, negative x. So the negative a times t, 0, 0. Right? So think about this as a rotating counterclockwise, then it will be this velocity will be pointing to the negative direction of xa direction, right? So this is the case, then I think that will be negative at 0, 0. That will be the answer. I use this very artificial example to illustrate the key subtleties in defining the twist or spatial velocity. Any questions? Fusen, do you have any questions?
我没有什么问题。
Okay, all right. Okay, I hope that clarifies some confusion. We spent some time almost reintroduce twist again. But next, let's do some similar jobs for screw motion and the screw axis. Okay, this is super confusing as well. For some people. Okay, let's look at screw motion. Screw motion, let's not think too abstract. Let's just think there's a screw. You somehow rotate the screw, will move, not only have a linear rotating action, it also move along the rotation axis, right? So screw motion is nothing but a combined angular and a linear motion. Okay, these two motions are combined in a predetermined way. Okay, the motion is driven by rotating. All you need to do is rotate. You don't need to do other things, right? Just rotate. Then the linear motion along the rotation axis happens automatically because of the thread in this screw, right? This is thread in the screw. A screw motion, and just think about, not think about twist or anything else, just think about physics or real life. A screw motion characterized by 4 parameters, or these 2 sets of parameters. The first one is this, and the second one is how fast speed. Let's decouple them again, right? So here, I would say the screw motion has a rotation axis, okay, which is defined by this S hat. In this case, I would say S hat is the rotation axis direction, and Q is a point on the rotation axis. So if you give me a point on the direct rotation axis and give me a direction vector, I can uniquely determine this rotation axis. So S hat, among those parameters, S hat and Q, this determines the rotation axis. What's the difference between rotation axis and screw axis? Axis is nothing but a what? A direction, and also a point in the direction that uniquely determines the particular this vector, right? But it's not a screw yet. These only have a rotation, right? And if the hat screw means we also have a coupled linear motion, which is determined by this h. By definition, this is called pitch, is linear speed divided by rotation speed or angular speed. Okay, that's defined here, angular speed, right? So this is really due to, right? This is due to the thread on the screw. Okay, because you have the thread, if you rotate, you will induce a linear motion. So I will say rotation induces the linear motion. Linear motion is not independently determined, it's really induced by rotation, linear motion. So if h equal to 0, h equal to 0, then we will have a pure rotation, right? If h equal to infinity, that's the convention, okay? You don't have it, but if that's infinity, that means we have a pure translation. That's a pure linear motion. Overall, so x s hat q, that's the rotation axis, coupled with the pitch, tell you how the linear motion is induced by the rotation motion. This is called the screw axis, right? Screw axis. What's the difference between screw axis and the rotation axis? The rotation axis only have the direction and the point on the rotation axis, and the screw axis is not only rotation but also tells you a coupled linear motion, which is specified by the pitch. Okay, so it's nothing but rotation axis plus pitch that make it a screw, right? And this tells you the axis. And theta dot, screw motion, you can rotate faster or slower, or it doesn't change at all, right? So theta dot really tells you how fast the screw rotates. Okay, you only have one action, just rotates. You can slow, you can rotate faster, and if you rotate, the motion will rotate and also move along the screw axis. Okay, that's the physical meaning of screw motion and screw axis. I hope that clarify a few things. Now let's dive into a little bit more details. Okay, the first fact I want everyone to know or to keep in mind is screw motion. I think that should be easy to accept for most of you. A screw motion is a special rigid body motion. Rigid body motion. Okay, screw motion is a rigid body motion. Okay, that's easy to picture. It's a rigid body. Screw is a rigid body. Its motion is a rigid body motion. So it has a twist. So we can describe the speed in terms of twist language, right? Let's pick a frame. Let's pick a frame again. Let's call it A. I think I marked it here. It's pick a frame A. Then I will say this tells us if you specify these parameters in the frame plus the rotation speed, we can, as I said, this is a special rigid body motion, so you have a twist, okay, omega and a V. And I didn't really write down, let's say A, that's fine. So that will be omega A is, by the formula we derived before, or it can be easily seen from the figure as well, omega A is nothing but the angular speed is the direction times how fast it rotates. Okay, as hat is the unit vector in the direction, and the VA is what? Is the velocity of the body fixed point, a point fixed to the screw axis, right? And currently coincide with OA, right? And in that case, it's nothing but, because it's body fixed point, I can select, let's select a point on, use intermediate variable, right? Intermediate variable is some point velocity, the velocity of a point on the rotation axis. So that will be V of Q, let's call it, let's directly write down the solution, okay? That's H theta dot S hat minus omega cross Q, right? So if I want to argue why this is the case, we can use Q as the reference point, okay? Because we know the velocity of Q, VQ, so VA, V of OA equal to VQ plus omega cross from Q to OA, right? That's the, if you have a body fixed point currently coincide with VOA, then VOA is VQ plus omega cross this vector. And we know VQ does not have rotation motion, only have linear motion along that direction. That linear motion, the speed is h times theta dot and s hat plus omega cross this Q to OA, and is actually the negative of Q in OA, the vector representation, right? If I say everything in A frame, then roughly we will have this, not roughly, we will have this formula. Let's call it A. Okay, so that's the formula. Let's call that, where's my equation number? I think it's, let's call that 5. Okay, that's a from a twist or spatial velocity, we can, sorry, from a screw axis or screw motion, we can find the corresponding twist. It's a special rigid body motion so that we can characterize it's a spatial velocity. I would like to write it in the following form. Okay, so given any this, I can compute the twist, screw to twist. This is a function. If you tell me S hat, tell me H, tell me Q, tell me H, tell me theta dot, I can compute the corresponding twist through formula. This is just equation. This is equation 5. Equation 5 tells you if you gave me the parameters in terms of this more kind of intuitive parameterization S hat, Q, H, and theta dot, I can compute the corresponding twist for you. Oh, that's a fact. Another fact is the following, is that any rigid body motion can be viewed or realized as a screw motion. This is 2 directions, right? The first one saying the screw motion is special rigid body motion. And the second one tells you that any rigid body motion can be thought of as a screw motion. Okay, it does not lose any kind of special cases. You cover all the cases for screw, rigid body motion. Can be viewed this way at least. In other words, given any, let's say, given any twist V, that's a twist, right? We can always find, we can always find, let's say always find our kind of natural parameterization of screw axis, which is S hat Q H theta dot, and such that equation 5 holds. In other words, so this function has an inverse. So it gave me the function value of twist. I can invert it to find S hat Q H and theta dot. Okay, this formula I don't want to repeat. That's in the model robotics textbook or in my lecture note too as well. Okay, the third one, so that means screw axis or screw motion and rigid body motion has 1-to-1 correspondence. Given the screw axis natural parameterization, I can find the twist. And given twist, I can find its corresponding screw axis and the speed theta dot. Okay. Another thing that's very important is the following: is by, let me use color, right? Okay. By 5, we know the following: V equal to screw to twist. That's a function, right? S hat Q H 1, if I put a unit speed, times theta dot. In other words, the expression here, both omega and the velocity is linear in theta dot. To see this more clearly, we also need to point out that this guy is what? S hat times theta dot, right? You can factor out that theta dot. You see what I mean? In this case, this guy is, if I say unit speed, rotating unit speed, I will have a corresponding twist, right? And this, I will call it, I can define it as S. Okay, while the notation is sometimes it's a little bit more confused. So I will write this as S times theta dot. That's where this expression meaning come from. Because of screw to twist this expression, it's linear in speed because of the formula, right? Then I can write something S times the rotation speed. In this case, this one is nothing but the twist corresponds to rotate at, let's say, screw motion characterized by S hat Q H and theta dot equal to 1 unit speed. Okay. If you have a screw axis, that means rotating and also coupled with a linear motion. If you rotate at angular speed 1 or unit speed, that will have a corresponding twist. That twist, we can call it a screw axis as well. Okay. So in this case, let me make some analogy. I'll take a break after I finish this part, okay? Insert pages. I think one is enough. Let me write here. Let me give example or make analogy. It's, let's say, we typically write a angular velocity as velocity. This is rotation axis, theta dot, right? This omega hat has two meanings, right? It tells you the rotation axis, the direction, but it can also viewed as the angular velocity when rotates, let's say when it rotates about the axis with speed at unit speed at theta dot equal to 1. Okay, so direction vector also can also viewed as a unit, right? Here is the same thing. Okay, given a twist, I can think of it's a unit screw axis, has a picture in mind, screw axis, and I use S to denote its normalized twist, almost like. So rotate about that screw axis at unit speed, then how fast you rotate just scales up your motion along that direction. Okay, let me summarize. Let's say given any rigid body motion or velocity, let's say motion, characterized by the twist as omega v. Okay, so that's a rigid body, and this is omega. There also some kind of v, right? Depending on where I select the origin, this v may have different meaning. Okay, if you picture graphically your mind, you will have two direction vectors, rotation vectors and also linear motion direction. There's a kind of two direction, right? So typically we'll say this is the angular direction, which is omega hat, or you have a linear motion direction, which is v hat. Let's say the directional vector of v, right? You have these two things in your mind. Okay, but now let's convert that to just one thing, right? Let's just think about, okay, let's think about this only one screw axis. Okay, you can think about that as a direction, or if that helps you, think about this similar as the omega hat. Okay. So this screw axis S will be, let's call it A screw axis, V screw axis. Okay. Oh, no, not S screw axis. Screw axis. I don't know, use this notation just for here to clarify this difference from the V omega, the omega and the V in the twist case, right? In your mind, just a one screw axis, just one direction, and there's a thread or the screw, so that there is a coupled motion, all right? And this thing is normalized. The corresponding twist is given by this S. Of course, this is, we can always, if we want, we can always convert to the more standard the axis S hat, H, and Q, right? And we can write the twist as the screw axis times theta dot. That's the whole meaning of screw axis. So that's exactly have the same kind of you can this is analogous to the rotation case. All right. So whenever you see a twist or linear velocity, the spatial velocity or real body velocity, you think always in your mind, think there's a screw axis, it has a coupled rotation and linear motion, and theta dot determines how fast you move down that direction, right? And we know how to compute everything involved. Okay, hopefully that's good enough for now, and I think now we can continue our other discussions. We will take a break. In the chat area, I think there's a student ask why in this example, why VA in B is 0, B is moving, right? This B is moving, and why VOA in B is 0. Okay, that's an interesting question. I think there's a, that's why I think it's worth time to go over this in detail, right? If you have those kind of questions, again, I would encourage you that to think in terms of coordinate free first. Let's say in coordinate free, let me use red color. Let's say in coordinate free, let's say VOB is VOA plus omega cross OA OB, right? That's a formula that's the same as we reviewed or even derived for parameterization of the body, any body fixed point. Okay, by definition, this is what? This is the velocity of body fixed point coincide, let me repeat that again, coincide with OA. Okay, so now you think OA is body fixed now, right? If the body fixed, what is its velocity? The student, can you answer my question, or I assume you're okay with this is 0. If not, please let me know. This is clearly equal to 0, right? This vector is 0 vector. It's body fixed point currently coincide A, so this A doesn't move. The rotation doesn't really kind of generate any motion for the body fixed point at OA. So this vector is 0. Okay, it's 0, 0, 0. This is the vector. Sorry, this 0 vector. That's not right. 0 vector. Okay. If I represent the 0 vector using whatever frame, it's still 0. Okay, that's why VOA in B is 0. It doesn't matter B is changing. I just represent this vector in B. If I already have a vector, then I can represent this vector in any coordinate. Now I happen to represent the vector in this coordinate B, but the B is changing, moving, it doesn't matter. At this moment, at any given time, I can represent any vector in B. And in particular, this 0 vector is coordinate B is 0. Okay, I hope that's explained.